Hello. Today we're going to look at how elements are made. In my video Reasons for Quantum Mechanics, I said that basic elements could not be manufactured. They can be combined to form compounds, but they cannot themselves be manufactured out of something else. So where did they come from? The Big Bang, which occurred 13.7 billion years ago and which created the known universe, basically just created the element hydrogen with a little helium. These are the two lightest elements. The universe was expanding, but gravity was at work on the hydrogen, which was expanding in the universe, causing the hydrogen particles to come together. As they drew closer together, the particles moved faster under the influence of gravity. But the faster they travelled, the more energy they gained, and the hotter they became. As the temperature increased, the hydrogen became a plasma. That is where the electrons have so much energy that they can escape from the atoms. In the case of hydrogen, that will just leave a proton behind. The weak interaction can convert a proton to a neutron. A proton and a neutron are made of quarks. I have described this in my video on the Standard Model. As gravity continues to work, the protons and neutrons get pushed together, and by various processes, two protons and two neutrons end up as the nucleus of a helium element. Normally it would not be possible for two protons and two neutrons to come together to form a helium nucleus, because the two protons would repel one another because of the electrostatic or Coulomb force of repulsion. But the core of the Sun is so hot, and the particles therefore have sufficient energy that they can overcome the Coulomb repulsion force and fuse together. This is called fusion. The ball of hydrogen is now a star. As I described in the video on the Standard Model, the process of converting hydrogen into helium releases energy. This is because the mass of two protons and two neutrons is slightly greater than the mass of the helium nucleus, which contains those four particles. The mass difference is converted into energy by Einstein's famous formula E equals mc squared. A huge amount of hydrogen is converted into helium, so a huge amount of energy is released, mainly as heat and light. The energy which is released creates a pressure which is sufficient to balance the gravitational forces which are trying to cause the star to collapse still further. So while the fusion process is working, gravity is held at bay and the star maintains its size. For most stars, that is all that happens for pretty much the entire duration of their life. Our own Sun, for example, is 5 billion years old. It still has another 5 billion years to go. Throughout that time, it is steadily converting hydrogen into helium. At some point, all the hydrogen in the core of a star has been converted into helium. The outer layers may still contain a substantial amount of hydrogen, but the main fusion process, which is holding gravity at bay in the core of the star, will stop. Once the fusion process in the core has stopped, gravity takes over again, and the star begins to contract. But as it does so, its temperature increases even further. And now, apart from the smallest stars, the helium in the core has sufficient energy to fuse to make higher elements in the periodic table. The periodic table sets out all the known elements in order of atomic mass. This essentially reflects the number of protons in the nucleus of each element. Depending how big and how hot the star is, the fusion process is capable of manufacturing elements by fusion all the way up to iron, which has 26 protons in its nucleus. This means that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese and iron can all be produced from this process. In each case, the mass of the nucleus of the element formed is smaller than the masses of the nuclei which were used to make it. The mass difference is converted into energy. But once we get to iron, the process cannot go any further, because now, in order to make elements that are heavier than iron, instead of energy being released as a consequence of the fusion process, we now need to put energy in to make the fusion process happen. And there just isn't that much energy around. So once stars have got to a point where their core is made of iron, assuming they can get that far and have enough energy to do so, the fusion process stops. Gravity once again dominates. The star quickly begins to collapse. What happens next now depends on the size of the star. For small stars, the gravitational collapse will be stopped by a process called the Pauli exclusion principle. Wolfgang Pauli was a physicist who discovered that two electrons cannot occupy the same energy state at the same time. That resistance by electrons to being in the same state is sufficient to stop gravity from causing any further collapse of the star. The fusion process has ended, and the star will continue to glow for many billions of years. It will be known as a white dwarf. Eventually it will cool down and fade from view. But for bigger stars, gravity is sufficient to overcome the effects of the Pauli exclusion principle in relation to electrons. The star's outer surfaces are collapsing onto a hugely energetic inner core, and this results in a cataclysmic explosion of astronomical proportions. It is known as a supernova. In what might be a matter of a few days, more energy is released from that star than from a whole galaxy that might contain 100 billion stars. The energy is colossal, and it is during this period that elements all the way up to uranium with 92 protons can be manufactured. So it is rather fascinating to think that the gold in my wedding ring was manufactured in a star, probably 8 billion years ago or so, at the time it underwent a cataclysmic explosion. The core of the star continues to contract under the forces of gravity. Atoms in the star are crushed. Electrons and protons are forced together to make neutrons. The neutrons are squashed together. There are no atoms and none of the space in atoms. The star becomes a neutron star. 1 teaspoonful of the material on a neutron star would weigh 500 million tons. The star is probably only the size of a city, and it rotates very quickly. The reason it rotates quickly is the same process that ice skaters use to rotate more quickly on ice. An ice skater may begin a spin with his or her arms fully extended, but as they bring their arms in, the spin gets faster. This is due to the principle of the conservation of angular momentum. Angular momentum is mvr, where m is the mass of the body, v is its velocity of rotation, and r is the radius of the body. Angular momentum must be conserved, so if the radius contracts, the velocity must increase to compensate. That is what happens with a neutron star. At this point, a different version of the Pauli exclusion principle comes into play. This stops two neutrons from being in precisely the same state. That will stop any further gravitational collapse. Unless the star is so massive that gravity can even overcome this one last barrier. If it does so, there is no known physics that will stop the star from continually contracting, becoming ever more dense, until it becomes a black hole. A black hole is known as a singularity because it has no spatial dimensions. The entire mass of a star is condensed into a space which is infinitesimally small. But what about the remnants of the supernova that have been exploded into space? Well, gravity takes over again and begins to draw them together until they form the basis of another star, and the whole process can start all over again.